So now we're going to start a somewhat tricky topic, and it's called implicit differentiation. Okay, so okay, let me just write it out here first. Alright, so what is implicit differentiation? We're here, so I guess it would be easiest for me to give you an example. Say I have this equation, xy is equal to 1. And I told you that I wanted to find dy over dx. What would you do? Looking for a pen here. There you go. There one. Okay, so you would first simply divide both sides by x, and then take the derivative, and you would be correct. However, say I told you, no, you're not allowed to divide through by x for some odd reason. Okay, so then what would you do? So here's a little trick. We can take this is what we're going to do. We're going to take the derivatives of both sides with respect to x. Okay. Now that's going to look kind of weird at first, but this is, just stay with me here. So we're taking the derivative of both sides with respect to x. Before we do that, let's review something. What does it mean to take something, to take the derivative of something with respect to x? What does that exactly mean? So, take a look at this here. We have the derivative of x to the fourth with respect to dx. Notice that the terms here are the same. We have x in the bottom, and we have x in the function. So therefore, we can simply use the power rule. And just bring that down, and then minus 1 from the exponent, 4 times x cubed. So what about if I gave you this thing here? What's the derivative of y to the fourth with respect to x? Well then, I would have to tell you another thing. Y is a function of x. Okay, so I'm telling you that y is somehow defined in terms of x, but I didn't give you how it's exactly defined. I'm just telling you that it's defined in terms of x. So can we do this? Yeah. Right? Because in the end, y can be somehow written in terms of x, but I just didn't write it out for you. So how would we go about doing this? Well, then I would still apply the power rule, but I would also have to apply the chain rule. And it's like this. So here, I'm still going to apply the general power rule, so bring that down. But once I'm here, I'm not done yet. Why? Because I still have to take the derivative of y. So that's my answer, actually. So here I'm assuming that my outer function is to the fourth, is raising whatever is inside to the fourth. That's my outer layer. And then my inner layer is y. So it might be a bit clearer if I wrote it in this non-conventional form. I have a function that's in terms of x, and then I'm raising it to the fourth. I'm asking for the derivative of that. So then I would first peel away the first layer, y to the third. Okay, now I peel away the first layer. Now I still have another thing inside. So then I have to take dy over dx. Okay. But then, can I continue? No, because I don't know. I'm stuck here. I'm going to stop here. That's fine. What about here? Why didn't we have this thing here? Well, we actually did, but we never really needed to evaluate it. So here we actually do have a chain rule. If you wanted, we could have written like this. Okay, so d over dx. Okay, so we're taking the derivative of x to the fourth with respect to x. So then the first layer would be to the fourth. So we do that. And then we have this inner thing, and then we have dx over dx. Okay, so there are two ways to think about this. You could think of it as a fraction, and then because we get the same thing in the top as in the bottom, it cancels out to 1. Is that the true reason? No. The reason is because you know that the derivative of x is 1. That's why this goes away. So do you see that? So actually, we do have somewhat of a chain rule here, but the thing is that dx over dx disappears, it goes away. But if we're taking the derivative of some other function that's not in terms of x, but in terms of another variable, we can also still take it with respect to x. However, we have to remember that we have to include this term in the end. So, do you follow me here? We're going to have this term here if this and this do not match up. Okay, so here we're taking derivative of x to the fourth with respect to x. So therefore, we have to peel away the first layer, which is this thing here, and then we have to still differentiate the inside thing with respect to x. So if you really wanted, you could write y of x to remind ourselves that y is defined in an x. But what about if I asked you, okay, to find the derivative of y to the fourth with respect to y? Then it would simply be, and since dy over dy is 1, y to the 4 times y to the 3, to the third. So, okay, so we learned here that only if the function is in terms of whatever we're taking the derivative with respect to, then does this thing disappear. Okay. However, if it's in different variables, we can still use some calculus. We use the power rule here, but we have to use the chain rule. And the chain rule tells us that we have to peel away the outer layer. So we can peel away the outer layer, but we still have this thing left here. Okay, so now with that in mind, okay, so let's do this here. Okay, that's kind of tricky, but follow me. We want to take the derivative of x to x times y. Okay, so x and y are two different entities. So then we have to use the product rule. So, okay, just ignore this. This is how it's going to go. We're taking the derivative of the first. Okay, so we have two functions here, x and y. And I'm telling you that y is implicitly defined in terms of x. I'll explain what that means later. But, okay, we have to use the power rule. So it's going to be the first times the derivative of the second plus the second times the derivative of the first. So first times the derivative of the second. Alright? So then it's going to be like this. Right? Plus the second times the derivative of the first. Well, the derivative of x with respect to x is 1. Okay, that's it. And then we're taking the derivative of a constant, which is 0. So now we see that we have x times dy over dx plus y equals 0. So we're going to solve for dy over dx. So then we bring the y over here. And then we divide both sides by x. Now is this? Almost. Okay, so then now we have to plug in for y. So we plug in for y here. So actually, now we have to solve for y. So if you solve for y, and you plug in 1 over x for y, you do get the same thing. So what did we just do there? What I just showed you was something called implicit differentiation. And in implicit differentiation, it's implicit because the derivative is defined in terms of both x and y. See here, we did not bother to solve for y before taking the derivative. We just took it, and we did that. Okay. On the other hand, explicit differentiation means that you first solve for y, and then you take the derivative. Well, why would we ever want to use implicit differentiation? Why would we ever want to use implicit differentiation? Well, the reason is sometimes it's too hard to solve for y, or sometimes we're just too lazy. But most of the time it's too hard. But I'm going to show you a case where we could solve for y if we wanted, but first we're not going to. Okay, so here's the graph of a circle. Circle is radius 1, the unit circle. So it's x squared plus y squared equals 1. So I want to find the slope on every point in this graph. So slope equals differentiation. So I'm going to take the derivatives of both sides of this equation. Sorry. There you go. So it's going to be dy over dx of x squared plus y squared is going to be equal to the derivative of 1 with respect to x. So let's do this side first. Well, we have x and x, so it's going to be perfectly normal. 2x. And then plus, okay, now we're taking the derivative of y squared with respect to x. So we have to use a chain rule. So first, we just take off the outer layer, so 2y to the first. And then we take the derivative of the inside thing, which is y. And then the derivative of a constant is 0. Okay? So, do you see what I did there? The derivative of 2x is equal to 2x. If you wanted to think about it, you could think of it as this way. And then, like this. You could think of it as that. And then we take the derivative of the inside thing, which is x. But we don't do that because we know that this is 1. So we stop there. We know that this is 1 because this thing is this, or in terms of the same variable. However now, this is not. So the derivative of y squared with respect to x is not in terms of the same variable. So we apply the chain rule. We take the derivative of the outer layer first, and then we plug this thing in. We add this thing to it. So if you wanted to think about it, you could think of it. We could think of it as pretending that this was x first, doing it, and then adding this thing at the end. Not the best way to think about it, but do you understand what I'm doing here? Okay, so we see that these two are not in the same, so we have to add this term at the end. Okay, so now my question was to find the slope at every point in this graph. So now I have to solve for dy over dx. Solve it over. Okay, divide both sides by 2y. So my answer is dy over dx is equal to negative y over x. Sorry, negative x over y. And that's my answer. So let's take a look at the graph of a circle. Wait, let me ask you, so say I wanted to find the slope at x equals 1/2, at x equals 1/2, comma, y equals root 3 over 2. So I'm looking for the slope at the point 1/2 over root 3 over 2. So then dy dx is going to be negative x over y. So then negative x over y is going to be negative 1/2 over root 3 over 2. Let's cancel that like that. So So it's going to be okay, yeah. It's going to be like this. It's going to be the square root of 3 over 3, and it's negative. Negative square root of 3 over 3. And if we take a look at the graph, so 1/2 going to be this point right there. Draw a tangent line in roughly. So about, right? Looks like it could be like this. And it is. Alright, so I showed you how to take a derivative implicitly. So here we did not solve for x, but we just immediately went ahead and took the derivatives of both sides. Now, if we wanted to solve for y, could we? Yeah. In this case, we could. Bring the x term over here, and then take the square root of both sides, plus or minus. Let me rewrite that. Like that. Okay, so then the derivative is going to be just do this out. Okay. And then this and this cancels. So it's going to be plus or minus, or so it's going to be the opposite sign, depending on which half of the circle you're using. X over root of square root of 1 minus x squared. Is this the same thing as this thing here? Well, let's see. dy over dx. If you plug in y, for x here, then indeed it is. Okay, so, yep. You do get the same thing if you solve for y and then take the derivative, but in this case, we just took the derivative. Alright, so there's some key points to take away with you. The first thing is knowing what the variable on the bottom means. D over dx. Dx, that means that we're taking the derivative with respect to x. So if we have if we're taking the derivative of this, we know that if we see an x term, we can simply use a regular power rule. But if we see a y term, we have to use a chain rule. We have to first take the derivative of the outside layer, and then take the derivative of the inside. Whereas here, we could still do the same thing, but we know that this is equal to 1. In the next lesson, we'll take a look at some more complicated examples. See you there.